A student carries out an investigation to identify two metals, M and X, by two different methods. Part A. The student is provided with a sample of metal M. The student analyses metal M using a back titration technique. The metal is reacted with excess acid. The resulting solution is titrated to determine the amount of acid remaining after the reaction. Stage 1. The student adds 100 centimeters cubed of 2.10 moles per decimeter cubed hydrochloric acid to 6.90 grams of M. An excess of hydrochloric acid has been used to ensure that all of metal M reacts. A redox reaction occurs, forming a solution containing M in the 2+ oxidation state. Stage 2. The resulting solution from stage 1 is made up to 250 centimeters cubed with distilled water. Stage 3. A 25 centimeter cubed sample of the diluted solution from stage 2 is titrated with 0.32 moles per decimeter cubed NaOH or sodium hydroxide. The sodium hydroxide reacts with excess hydrochloric acid that remains in stage 1. The student repeats the titration to obtain concordant titers. Titration results. The trial titer has been omitted. The burette readings have been recorded to the nearest 0.05 centimeter cubed. Part 1. In stage 1, a redox reaction takes place between M and hydrochloric acid, forming hydrogen and a solution containing M in the 2+ oxidation state. Write an overall equation with state symbols for this reaction. Write half equations for the oxidation and reduction processes. So, starting with the overall equation, we know that we have M and HCl, or hydrochloric acid, reacting together to form hydrogen and a solution with M in the 2+ oxidation state. So our reactants are pretty straightforward. We have M as a solid because it's a metal, and then we have hydrochloric acid, which will be aqueous. And then we're going to form hydrogen, which will be a gas, and then MCl2, which will be an aqueous solution. So now we just need to balance the equation, and in order to do that we need two hydrochloric acid components. So now we need to look at what's being oxidized and what's being reduced. So oxidation is the loss of electrons, so that means its oxidation state is going to increase. So the oxidation state of metal on its own will be 0. In hydrochloric acid, hydrogen will have a +1 oxidation state and chlorine will have -1. In hydrogen gas, hydrogen will have an oxidation state of 0. And then in the solution, we'll have the 2+ M oxidation state and chlorine will have -1 oxidation state. So the oxidation, the loss of electrons, is going to be metal M. So it starts off as M and then it becomes M2+ with 2 electrons because we've lost these 2 electrons. Reduction is the gain of electrons, and that means its oxidation state is going to decrease. So that's going to be hydrogen because we start off as hydrogen being positive, and then we're going to add an electron and we form half H2. Or we can double this, so 2H plus 2 electrons will produce hydrogen, which better matches the overall equation. To get the 3 marks for this question, you get a mark for your overall equation, a mark for your oxidation half equation, and a mark for your reduction half equation. And you can write either of the reduction half equations that I've written here. Part 2. In stage 1, suggest 2 observations that would confirm that all of metal M has reacted. So we know that in stage 1 we produce hydrogen gas. So our first observation is that the bubbles or the effervescing is going to stop. You could also say that the fizzing stops. The second observation is that we know we've got metal M, and that's a solid, and we're turning it into an aqueous solution. So our second observation is M, or the metal, is going to disappear, or you could say dissolves. So to get the 2 marks for this question, you get 1 mark for saying that the bubbles or the effervesces or the fizzing, that's going to stop. That's your first mark. And then your second mark comes from saying M, or the metal, disappears or dissolves. Part 3. In stage 3, write the ionic equation for the reaction taking place in the titration. So if we take a closer look at stage 3, here is the equation for stage 3, and we've got a base, which is our sodium hydroxide, reacting with an acid, which is hydrochloric acid, and that's producing a salt and water. So this reaction is a neutralization reaction where you're turning a base and an acid into something neutral, like water and your salt. So the ionic equation for a neutralization reaction is you have your acid, which is H+, plus your base, which is OH-, and you produce water, which is H2O. To get the mark for this question, you need to write this ionic equation out completely, as I've written it here. Part 4. Metal M can be identified following the steps below. 1. The amount in moles of excess hydrochloric acid that remains after the reaction of M with hydrochloric acid. 2. The amount in moles of hydrochloric acid that reacted with M. 3. The identity of metal M. Analyse the results to identify metal M. So let's start this question by highlighting the key pieces of information. So that's the volume and concentration of hydrochloric acid, the mass of M, that we've made our solution up to 250 centimetres cubed, and that we take a 25 centimetre cubed sample, that we're titrating with 0.32 moles per decimetre cubed of NaOH, and our titration results. But we only care about the concordant results, so we do need to work out the titers first and then look at which ones are concordant and take these to work out our mean titer. So if we work out our titers, and that's going to be centimetres cubed, we minus the final reading from the initial reading. So for titration 1, that's 27.30. For titration 2, that's 27.55. And for titration 3, that's going to be 27.20. So always writing to 2 decimal places when you do titration results, and that's so that you keep with the units of the burette and the table as a whole. So now we work out our mean titer. So the mean titer is taking the concordant results and dividing by how many concordant results there are. So that's going to be titration 1 and titration 3. A concordant result is within 0.10 centimetres cubed from each other. So the mean titer is going to be 27.30 plus 27.20 divided by 2, which equals 27.25 centimetres cubed. So now we're going to use an equation triangle. The equation triangle we're going to use is the number of moles is equal to volume times concentration. And what we're going to do is we're going to work out the number of moles of sodium hydroxide. So we've got its concentration and we've got its volume, which is the mean titer, so we can work out moles. So we're going to do 27.25 times 10 to the negative 3 because we convert centimetres cubed into decimetres cubed, and then multiplied by 0.320, which is the concentration of sodium hydroxide. And that equals 8.72 times 10 to the negative 3 moles. But this is going to be in our 25 centimetre cubed sample. But we have a 250 centimetre cubed solution that we've made from our original mass of M. So we need to factor this in and multiply by 10. So we do 8.72 times 10 to the negative 3 multiplied by 10, which equals 8.72 times 10 to the negative 2 moles in 250 centimetres cubed. So now we have the moles of sodium hydroxide in our resulting solution, and we know that it's a 1-to-1 ratio, so this can also be the moles of hydrochloric acid in our resulting solution. but we need to work out the initial moles of hydrochloric acid in order to work out our excess. So using the equation triangle again, we have our volume and concentration of hydrochloric acid in stage 1. And that's going to be 100 multiplied by 10 to the negative 3 times 2.10, which equals 0.210 moles of hydrochloric acid originally. So we can work out our excess by minusing these two numbers. So we do 0.210 minus 8.72 times 10 to the negative 2, which equals 0.1228 moles. And that is the moles of hydrochloric acid that's reacted with M. So we know from the part 1 equation that we have 2 hydrochloric acids for every 1 M. So we need to divide this by 2 so that we can work out the moles of M that's reacted. So that's going to be 0.1228 divided by 2, which equals 0.0614 moles of M that's reacted. Now we're going to use a second equation triangle. And this is going to be our equation triangle where we have mass is equal to the number of moles times relative formula mass. Or in this case, it's going to be relative atomic mass because we're only working out the relative atomic mass of the metal. So the way we're going to do this is we're going to take the mass of M, which is 6.90, divide it by the moles of M that's reacted that we've just worked out. And that is following step 2, which has asked us to work out the number of moles of hydrochloric acid that's reacted with M, which we have done, and then we've scaled it by dividing by 2, and that's using our equation that we wrote for stage 1. So now we're dividing by the moles, which is 0.0614 moles, and that's going to equal 112.4 as the relative atomic mass of M. So then we refer to a periodic table, and 112.4 is the relative atomic mass of cadmium, or Cd, which we can write as our identity of metal M. So to get the 6 marks for this question, you get a mark for working out your mean titer, you get a mark for working out the number of moles of hydrochloric acid in 25 centimeters cubed, you get a mark for working out the moles of hydrochloric acid in 250 centimeters cubed, you get a mark for working out your moles of hydrochloric acid that's reacted with M, so following step 2 of the list, and then you get a mark for working out the number of moles of M that's reacted. And finally, you get your 6th and final mark for identifying metal M as cadmium. Part B. The student is provided with the carbonate of an unknown metal, X2CO3. The student measures the mass lost when the X2CO3 is reacted with an excess of hydrochloric acid. The equation is shown below. The reaction is carried out using this method. Step 1. Add 100 centimeters cubed of hydrochloric acid to a conical flask and weigh. Step 2. Add X2CO3 to the conical flask and immediately reweigh. Step 3. After 5 minutes, reweigh the conical flask and contents. The results are shown in the table below. Part 1. Calculate the amount in moles of CO2 released in the reaction. So the equation triangle we're going to use to answer this question is the one from the previous question where we have mass is equal to moles times the relative formula mass. So firstly we need to work out the mass of carbon dioxide. So that's going to be minusing these two masses. So in the 5 minutes, what's happening in the conical flask is carbon dioxide gas is going to be expelled and you're going to see a bubbling or a fizzing happening. So if we minus these two masses, we've got 187.50 minus 184.75, which equals 2.75 grams of carbon dioxide. Then we need to work out the relative formula mass of carbon dioxide. So it's going to be 2.75 divided by 12 plus 16 times 2, which is equal to 44. And that's going to equal the number of moles of 0.0625 moles of carbon dioxide, which we can write on the answer line 0.0625. To get the mark for this question, you need to write 0.0625 on the answer line. Part 2. Calculate the molar mass of X2CO3 and identify metal X. So firstly, we need to note that the molar ratio of our carbonate to our carbon dioxide is the same. So that means we've got the same number of moles. So we can carry that on from the previous question, 0.0625 moles of carbon dioxide or X2CO3. Then we're going to use the same equation triangle that we've used in the previous question of mass is equal to moles times the relative formula mass. So we need to work out the mass of our carbonate first, and we do that minusing these two masses. So the difference in these two masses is that one has our carbonate and one doesn't. So if we minus these, we've got 187.50 minus 172.93, which is equal to 14.57 grams of X2CO3. So we can work out its relative formula mass or its molar mass by doing 14.57 divided by 0.0625, which is equal to 233.12 grams per mole. So that's our molar mass, which we can write on the answer line, 233.12. Now we want to work out the identity of metal X. We're going to do this using the molecular formula of our carbonate. So what we want to do first is minus the molar mass from the relative formula mass of our carbonate ion, which is going to be 12 plus 16 times 3. And then we want to divide by 2. And that's because we have two X's in our molecular mass. So dividing by 2 will give us the relative atomic mass of 1X. And that's going to be equal to 86.56 grams per mole. But this isn't the relative atomic mass of any element on the periodic table. Instead, it's between two. Now, in order to work this out, we want to work out the charge that X has in the carbonate. So a carbonate ion has a 2- charge, and there are two X's, which means that each X will have a +1 charge, and there's going to be two of them. So we're looking for our element in group 1 of the periodic table with a relative atomic mass closest to 86.56. And the closest one to this is rubidium. So its actual relative atomic mass is slightly lower than 86.56, but it is the closest group 1 element. Then, to get the 3 marks for this question, you get a mark for working out the moles of your carbonate, you get a mark for working out the molar mass of your carbonate, and then you get a mark for identifying metal X as rubidium. Part C. After analysing the results, the student was told that their molar mass of X2CO3 was incorrect. The student evaluated the experiment for possible reasons for their incorrect result. Part 1. The student wondered whether the reaction was complete when the mass was recorded after 5 minutes. Step 3. How could the student modify the experimental procedure to be confident that the reaction was complete? So this is a very common practical question, and the answer is that you reweigh to a constant mass. So when it's a constant mass, that means that no more carbon dioxide is being produced, and so when there's a lack of carbon dioxide being produced, that means that the mass is going to stay constant and your reaction is fully complete. To get the mark for this question, you need to write this statement, reweigh to constant mass. Part 2. the student finds out that carbon dioxide is slightly soluble in water. State and explain how the solubility of CO2 would affect the calculated molar mass of X2CO3. So I'm going to lay this question out as 2 bullet points, and each bullet point is 1 mark for this question. So the first bullet point is that the mass of carbon dioxide lost would be smaller. Alternatively, you could say that the mass of the carbonate, so X2CO3, reacted would seem to be less. So either of these statements will get you your first mark for this question. Then if we look at our second marking point, so our second bullet point, that is that the molar mass would be greater. So that's how you get your second mark for this question. Molar mass would be greater.